Hello everyone, my name is João Henrique and this is my oral presentation for the 26th International Congress of Mechanical Engineering, titled Dynamic Analysis of Rotating Systems with Vibration Absorbers. To begin, it is valid to state that rotating machinery presents inevitable mass imbalance due to its geometric and manufacturing characteristics. This imbalance creates an harmonic load acting on the rotor, which will then cause lateral vibration on the system. Vibrations are often undesired because they cause several problems to the machines. This work proposed 3 vibration absorbers which are assembled directly to the rotor, instead of traditional absorbers coupled on the base or foundation of the structure. The approach used has the advantage of attenuating the vibration directly on the rotor before it is transmitted to other components, such as bearing and foundation. Computational simulations presented in this work are made using commercial finite element method software ANSYS Workbench and its rotor dynamics capabilities. After assembling the global matrix, this is the general motion of equation for rotating systems, where mg is the global mass matrix, cg is the global damping matrix, gg is the global gyroscopic matrix, and kg is the global stiffness matrix. This is the imbalance force expression, where F is the product of mass imbalance moment and the square of rotational velocity of the rotor. Expressing the degree of freedom vector as a complex coordinate, we made the derivative to find velocity and acceleration. We may then substitute these forms of displacement, velocity, and acceleration back in general motion of equation from previous slide, finding unbalanced response equation. From unbalanced response equation, we can obtain both the amplitude and phase in the frequency domain, and these results are usually shown in the form of a Bode diagram. Rewriting the general motion equation previously described in the state space form, we find the system dynamic matrix A. Modal parameters such as natural frequencies, damping factors, and vibration modes are calculated from the eigenvalues and eigenvectors associated with the system dynamic matrix A. Since the dynamic matrix depends on rotational velocity omega, it is expected that modal parameters also depend on the system rotational velocity. Dependency of natural frequency and rotational velocity can be seen on the Campbell diagram. The rotor used in this work is a dual J-thin shaft supported by simple ball bearings, as shown in this slide, and this one is simulated with mass imbalance of 1 gram at 100 mm eccentricity. These are the rotor dimensions used in this work. Bearings are inserted in the model using ANSYS COBEM2021 element, which acts as a combination of springs and dampers, and can represent bearings from its equivalent stiffness and damping factors. On the right side, we can see a table with the equivalent coefficients used in the simulations. This slide shows the unbalanced response at disk 1 for the original rotating system used in this work. This slide shows the unbalanced response at disk 2, and in both disks the greatest amplitude occurs at approximately 28 Hz. As shown in previous 2 slides, greatest vibration amplitude occurs at 28 Hz. Campbell diagram shows this is the second critical speed of the system, which represents the first mode with forward whirl. Several geometries of absorbers have been studied via modal analysis using ANSYS, and 3 concepts were selected for presenting natural frequency closer to the second critical speed of the rotor. Modal analyses were performed with the inner diameter of the absorber bar constrained as a fixed displacement, since it would be attached to the rotor. This is the first concept selected, named helix absorber, due to its helix-shaped blades which act as springs. The second vibration absorber is shown on this slide, and it's named lateral pendulum absorber. Last but not least, there's radial pendulum absorber, and all the 3 concepts were tuned for a natural frequency of approximately 28 Hz, so it is expected that its resonant mode occurs when the rotating system approaches its second critical speed, thus concentrating its vibrational energy on the absorber's secondary mass, in this case the pendulums. The absorbers were then assembled at the free end of the rotor as a solid body and as a concentrated point with equivalent mass and inertia representing the absorber. This slide shows the result for a helix absorber for the case with single concentrated absorber at free end, dual concentrated absorber at free end, single solid body absorber at free end, and dual solid body absorber at free end. This is the result for lateral pendulum absorber, again as a single solid body at free end, dual solid body at free end, single concentrated absorber at free end and dual concentrated absorber at free end. The objective of plotting the results for both real solid dynamic absorbers and also its equivalent mass and inertia as a concentrated single point is to evaluate if the change of the dynamic behavior of this rotating system is due to its variation in total mass and inertia or if it's caused by the vibration absorber effect. This is the result for a radial pendulum absorber. For all three absorbers, it is possible to see that the concentrated point with equivalent mass and inertia barely affects the responsible rotating system, showing that the change of the dynamic behavior is really caused by the absorber effect. Also, the case with two absorbers show greater impact on the rotating system when compared to the case with single absorber. This statement can be explained by the fact that with more absorbers, there is more mass available to concentrate vibration energy in itself, as expected. In order to compare the absorbers' concepts between themselves, the results of real solid absorbers have been overlapped. In this slide for the case with single absorber at free end, from where it's possible to see that helix absorbers show the best results overall, with a wider band gap. The same comparison is made with the case for dual absorber at free end, and once again, helix absorber creates the widest band gap among other concepts, around 28 Hz. Since helix absorber has shown the best result overall, it was chosen for further analysis. In this graph, we can see the amplitude vibration on disk 1 for different placements of the absorber on the rotor, where 1 Fe represents single absorber at free end, 2 Fe represents dual absorber at free end, 1 Fe, 1 C represents one absorber at free end and one absorber centralized between the disks, 1 C represents one absorber centralized between the disks. It is possible to see that cases with two absorbers have more impact on the system than cases with one absorber. This can be explained by the fact of having more mass available to vibrate and concentrate energy. This graph is analog to the previous one, but showing the amplitude on disk 2. Besides the impact of having more mass, it is also visible that placing the absorber centralized between the disks show greater influence than placing the absorber at free end. In practical application, however, this position must be considered carefully due to spatial constraints on the rotor. In this paper, three concepts of dynamic vibration absorbers were proposed in order to reduce vibration amplitude of a rotating system operating close to its second critical speed. All three absorbers were capable of reducing amplitude levels on the desired frequency, creating a band gap around 28 Hz. Helix absorbers showed the best result overall, with a wider band gap. Results also show that heavier absorbers cause more impact on the system because they have more mass available to concentrate vibration energy. Placement position also affects the dynamic response of the system, and the best position so far is the absorber centralized between the disks. However, this placement must be considered carefully in practical applications due to spacing constraints on the rotor. However, placing the absorber at the free end still shows great results. The authors would like to acknowledge and thank National Council for Scientific and Technological Development, CNPq, and the University of Campinas, UNICAMP, for infrastructure and financial support. Thank you very much for your time.